so what we're going to do here is describe tuples of length n. And so this type is going to be dependent on this value n. Okay. So what I'm first doing is I'm writing down an example of one of these b functions, which is a type that depends on some value. Okay. And this one's recursive, and I can just use what we've already got going with the lambda calculus and the y combinator to write down a function that's going to take a number. If that number is 0, it's just going to be the unit type. So this feels kind of weird that we're writing down functions that produce types. Okay. If the n is not 0, then it's going to be the type of natural numbers cross the rest of the type that we're going to compute recursively with n minus 1. Okay, so if I were to take like nat vector of 2, that would give me nat cross unit. Okay, for example. Okay, so this is a sort of a function over types. That's what these b's look like. Okay. So now let's ask, well, what does one of these pi types look like? And what would be a lambda term that has one of these types? So let's talk about pi of n nat, okay, and then nat vector of n, okay. So this is going to be the type for functions that take a natural number and then produce something that is a n-length tuple. Okay, so let's go ahead and create a lambda term that has this type. Okay, so one example is what I'm going to call it the zeros function, and it's going to produce a tuple, kind of boring, but it's going to be a tuple full of zeros, but it's going to have the n as its length. Okay. So it's going to be, again, we'll need the y combinator for this. So if n is 0, then we better produce something of type unit. Okay. So that's just, an empty thing. Okay. The empty sequence. If it's not, then I need to produce something that's nat cross, something of one smaller. So I'll produce a nat I'll produce 0, and then I'll need to do the recursion at n minus 1 to produce the rest of it. Okay. So this whole thing, let's call that function zeros. Oops, got carried away there. The zeros function, it has this type. And if I say zeros 3, I'm going to get 0, 0, 0. Actually, there's a few more parentheses in a unit, but you can sort of ignore those. And so you get a 3-tuple of zeros.
Yeah, it's sort of like you'll want many times to take the dimension as a parameter and then have things that would work over all dimensions or something like that.
Let's say you're doing matrix algebra and you want to make sure you get your, the matrix dimensions lining up when you do matrix multiplication.
Yeah, so you won't be working with just a particular size matrix, but be working with arbitrary matrices of any size. Yes.
Question?
V of n minus 1, that V is referring to the lambda V.
Yes. And this is just the recursion. If you remember the y combinator, you get a copy of yourself.
Start over. Okay.
Duplicate this, do it again, but with n minus 1.
Okay, let me go on here. The next thing is generalizing to sums. When we took the binary sum, that meant we just had two different kinds of things, and we tagged them with a 0 and a 1 to make sure that we have representations that are disjoint. And now you can, if you want to go on, you can just as well use arbitrary tags of any type, and that will just give you lots and lots of copies of whatever the things are, where the kind of object that you are typing depends upon the tag. Before, there was no dependence on the tag because we just had one or the other, but now we could make it easy to depend on the tag. So again, you can write these things down using the logic of relations and equations, like equations representing finite sequences, or taking pieces of finite sequences, or things like that. And for example, a special case there is that the product of two things is just the A copies of B in a way. And so if you look at what sigma of type A, X of type A, B, all the same there, that's just ordered pairs of A and B. And so sigma is a generalization of product when you're thinking of constant families like that. But of course, there are lots of other properties that sigma has, because there's all kinds of associative properties, because you can reorder your parameters, and there'll be all kinds of awful formulas to relate different kinds of sigmas to each other. But now if you're going to compound sigmas and products and sigmas and products, and this is what people do in dependent type theory, you have to make sure that you have coherence from stage to stage of the types there. So now a system of dependent types means B depends on A, so equivalent parameters give equivalent results. C then depends upon both A and B. But you see there are more parameters there to keep track of there, because you have to think of several entries there. And again, these are not symmetric definitions, so proving that these are symmetric and transitive relations takes a little effort. Maybe I should have made fun of teaching predicate calculus. We know lots of people. I have very fine colleagues who are doing automated theorem proving. So they could easily just put these theorems into an automated theorem prover, and they would get the answer back in a couple of seconds there, because they're not complicated theorems of predicate calculus. And then, of course, if you go on, D there has to depend upon parameters from the A's, the B's, and the C's, and you have to make sure that equivalent things give you the right equivalent things. And then, if you have all that coherence, you then have to prove that the gigantic, now that's really a gigantic formula in logic, and I guess we better leave it to the automated theorem prover to do it. The product over A of the sums over B, of the products over C, of the D's that depend upon all of those parameters, is miraculously, again, a partial equivalence relation, is a type. It makes sense. And now you start thinking here, now wait a second, it means whenever I take something of A, I can choose something from B, such that no matter how I choose from D, I'll get something that does something there. That's sounding very much like predicate calculus itself. And so, in fact, we can give an interpretation of predicate calculus. I had a little example here of polymorphic types, but I'll return to it later. If I start thinking of these combinations as to say how I put them together and what does it mean, it really means that I'm doing trying to establish a logical fact that with this coherence I can actually find things that are structured in the way that was advertised there. So actually, if you think of one of these type expressions, you can say there's a proposition, a statement connected with this, which is that there actually is something that has that type. This is a kind of interpretation of logic where you give through these formulas with the pi's and sigmas and all that, you put down the dependence there, and then you have to check that actually something following through that dependence actually gets to the end without any confusion on the types there. And so you can think of it this way here, is that finding an E of a certain type is giving evidence that that type, the statement that that type is non-empty. And so those are very interesting assertions to say, yes, I know that that type is non-empty. For example, if I had a binary operation on type A, and if I use the type of identity with respect to A, that's just the equivalence relation A itself there, and I make a parameterized type there by using F, an application there, thinking of F as a binary operation, I can say, what does it mean for F to be an associative binary operation? And of course, what it means is, first you compute it in one order, or then you can compute it in the other order, and they have to be equivalent results there. But you see, that notation there, equivalence of A, that's in my type system here. Application, of course, is allowed because I'm using my underlying lambda calculus model all for writing those things out there. When I said F was a type A arrows A arrows A arrows A, then that really I'm thinking of just any typical example where I have a binary operation that I'm calling F, except when I write out formulas of it, I have to follow the notation of the lambda calculus and use F of X over Y that way. But now if I take pi over A, pi over A, pi over A 3 times there and say, is there evidence that we have a associative operation? Then we have something to work on there, because that evidence is a program that verified an assertion, and you can then use that verification to verify other insertions by, in other words, you're remembering the proof in terms of what you can write down in the lambda calculus, and then you can reuse that proof for proving other assertions there too. So this is, in a little bit, functional programming being applied to finding evidence, and we're using the lambda calculus notation and maybe products and sums there to structure these things there. And so we're combining functional programming with proof checking. And so you can think of that as saying that products is like conjunction, because finding evidence for P cross Q means, oh, I know evidence for P and I know evidence for Q. Finding evidence for plus means, well, either I found evidence for the first or the second, and I know whether I found the first or the second there, because finding evidence, I have to get those tags, the zeros and ones, along with it. That's part of the evidence there. Now the function space, this is many people, and Curry started thinking about it already in the 1930s there. The function space corresponds to an implication, because finding evidence in the function space means whenever I might be able to find evidence for P, I would automatically be able to find evidence for Q. It doesn't mean I can decide whether P or Q is working out or anything, but I have a general procedure already stored away, so that were I to find evidence for P, I could immediately use that to get the evidence for Q. And so that's the idea of implication, and of course the pi's and sigmas are just universal and existential quantifier, and you can see the quantifiers in the definitions directly, the way that I gave them. And so what we have out of this then is that the power set of n model is one model that combines a lot of things to think about. It has topology. Types can be thought of as coming from subspaces, and then the types inherit the topology automatically. They also, because certain kinds of enumeration operators are what we mean by the computable functions in this universe, then the types also inherit ideas of computability. It's not always easy to tell if there is computable evidence for a certain assertion, but in some cases it's possible, and then you have more information than you might otherwise have. And I didn't say things about polymorphism. I'll go back to that. And so what has turned out here, and people arrived at this in many different ways. Kleene started it by trying to interpret constructive logic in terms of what he called realizability things, realizability interpretations, and he did two big projects in that, one for arithmetic and one for analysis or second order arithmetic. But it turned out that there are many other examples too, and it's closely related to things that people do in category theory too, because we have been just talking about one very rich category, but there are lots of categories out there in the swamp waiting for you. So these ideas have come up in many different kinds of ways, and it's turned out that in trying to understand how these dependencies can be sorted out, you really have to follow principles of intuitionistic logic. You see, you don't always have a decision method of saying either something is achievable or it's not achievable. And so when you do this kind of functional programming here, you only can work on the information that you have, not on the information that you don't have. And so it turns out that thinking about what things can be worked out this way with these definitions is an exercise in understanding constructive or intuitionistic logic. But more, there are other kinds of recursion possible too. And so I mentioned something about polymorphism. So for example there, the pair combinator, where you take the pairs on power set of n there, the pair combinator has many different types. No matter what A and B you choose there, it will always have type A arrows B arrows A cross B. A very interesting question, and I don't think I can solve the question, is what other elements of the type, the intersection of all those function spaces over all A and B, are there any other elements of that polymorphic type? It's polymorphic in the sense that things satisfy being of a type over many, many, many different choices of types, but it's the same arrangement from A to B to A cross B. So polymorphic means no matter what A and B are, you'll always be okay with that lambda expression. Are there any other lambda expressions? I leave it to you to figure out what are the types of the Church numerals. You know, identity function is polymorphic A arrows A. What are the other numerals? How do they work out there? So there are a lot of questions to work out with those. Now, the Church numerals as iterators were quite annoying because it took Kleene Claney said he had to go to the dentist while he was working on his thesis. He went to the dentist, and the dentist had him in the chair. He then realized how he could do predecessor by the stage computation there. So sometimes you need to be put under distress in order to get a good proof. But it always annoyed me that it took effort to get the predecessor operator out of there. Church was very proud of himself because he got addition, multiplication, and exponentiation with simple-minded combinators. But then it occurred to me once, and then later on, Claney wrote me and said, oh yes, that had occurred to him too. But at the time, Church wouldn't let him change his thesis there because Church wanted only his iterators as numerals because they were so perfect in themselves. But you can make up other data structures where in the data structure for the integer n, you store in the integer n minus 1 as part of the data structure. And so therefore it's trivial to compute predecessor there because n already contains all its predecessors if you just start pulling things apart. And so someone pointed out that the numerals that I thought of there back in 63 are in a polymorphic type. Now here's an interesting point that's connected with a question about different kinds of domains and things like that. The types don't form a domain because they don't have finite approximations, but the types are just partial equivalence relations. Being a partial equivalence relation is defined by universal quantifiers. So it's a very simple proof in logic to say arbitrary intersections of types are types. Intersections of no matter how many of equivalence relations are still symmetric and transitive because the property of reflexive and transitive is given by a universal quantifier, and an intersection of many types is just a quantification, universal quantification over the types. And the universal quantifiers greet each other very happily, and arbitrary intersection of partial equivalence relations is always a partial equivalence relation. Now, the thing there is that the types form a complete lattice. They are partially ordered because you can say one partial equivalence relation is a subrelation of another equivalence relation, so there's a partial ordering there. But because it's closed under arbitrary intersection, that partial ordering makes it into a complete lattice. And now it's an old theorem of Tarski and his colleague Knaster back in the 20s. I still met Professor Knaster on a visit to Poland once there. They proved that on a complete lattice, any monotone function has a smallest and largest fixed point. But it has to be monotone to work out. When we worked with closure operators, the closure operators form a complete lattice, but amazingly, when I take C arrows D, it's monotone in both C and D, and so I was able to work out D equals D arrows D, because monotone functions have fixed points. When you go to types, the arrow operation is no longer monotone, because if you think of the type from A to B, if there are more B's, there's more. But if there are more A's, there's less, because the things go the opposite way. So it's not a monotone operation. However, if you take this dependence, this functional dependence there, where Scott occurs in Scott arrows A, then Scott is in a monotone position. And so there is a least fixed point in the category types. What it actually is, I mean, it's very nice that Scott's numerals would have that type. But of course, once you get up to these sets of sets of sets, and complete lattices and arbitrary intersections, it may be pretty hard to figure out what you get there. But there are a lot of simple statements that can be done. Polymorphism is interesting in trying to understand how maybe type checking works out, or other things of giving you some experiments with types depending upon variable parameters somehow. So there's a lot of fairly easy things to work out there, but as it often happens, a simple definition may give you a lot of effort to really understand what you manage to define. The definition itself says it means something, but proving all the properties you might need of it is a long thing here. So now polymorphism with type constructors, and if you're careful to look at those that are monotone there, then by taking least fixed points and greatest fixed points, you have a start in thinking about inductive types and co-inductive types. Of course, when we did the least fixed points in the lambda calculus, everything stayed computable. When you do these least fixed points in the type theory, in the lattice of types, it's infinitary. Things become much more complicated than just what you get out of the simple recursions back in the lambda calculus. But what I tried to emphasize here, by starting with a power set and thinking about topology and thinking about numbering, you get into a pretty rich area, and I like to think of it as a laboratory in which you can really ask some questions and to see what's happening. It's not the only laboratory. There'll be many competing ones, and the category theorists are coming up with new ones every day, unfortunately. There are lots of other places to experiment with these things, but I think that the power set of n, it should be easy to understand how to think of relations and functions between integers, sets of integers, sets of integers. That's my message. I'm going to stop early today because we've went through an awful lot here. I'm glad we could answer so many questions. I'm certainly happy to answer more questions now, but I didn't want to go on to any other materials now. So questions, please. Go ahead.
So this idea of thinking of types as partial equivalences, I think I've seen this before. I'm wondering if there's a connection with the proof of the parametricity theorem.
Yes, those things. Yes, those. Yeah, people are using it all over, but it's an old idea. Eric Bishop, who was a very amazing mathematician whom I also knew very well at last, was taken by cancer. When he wrote his constructive analysis, he was using those same ideas there too. He was raised in the Chicago School of Functional Analysis, and they worked with all kinds of monster types and ultrafilters and all kinds of things. And one day Eric Bishop said to himself, all of this abstract mathematics has no numerical content. How do you really keep track of any kind of specificity in the way things are made up? And so that's what made him start thinking about constructive analysis there. But of course, he understood too that these partial equivalence relations is exactly what you need to think of many standard mathematical structures in constructive analysis. He uses them, and lots and lots of other people in type theory are using it. So it's really not a surprising idea. The trick is to find nice definitions for making compound things and then really doing the proofs to show that the things have the properties you hope they have. So it's not the idea of partial equivalence relations that needs cleverness. It's the finding the right partial equivalence relations where the cleverness is needed. Other questions? Yes?
What is a lattice? And I understand what a fixed point is, but I don't understand what a least and greatest fixed points are.
Okay. You know, my friend, I'm not going to answer that question. I've met many times the famous physicist Freeman J. Dyson. He said the other day, all of my colleagues complain about Wikipedia, but all of them use it. If you put into Google search lattice wiki, you will come up with another. Of course, a lattice can be something you find in the garden as, you know, a lattice structure. But maybe if you say lattice math wiki, it will give you pretty nice definition. Actually, Wikipedia has been doing very well. I found a lot about to remind myself of those topological definitions just by looking them up on Wikipedia. So answer your questions for yourself, please. But if you want to ask another question, I'll listen to it. Do you? Another question? Anyone?
Yes, if you did meet Turing today, what would you say to him?
I think the thing that he would have the most interesting comments on relating to his own experience from his childhood is what's wrong with our educational system and what can we do to make more creative people. I think he would have 100 things to say about creation of things. You know, he thought about very complicated things in numerical analysis. He thought about biology. He thought about artificial intelligence. And the whole question is, how do you, you know, grab something that then is creative when you do it? So I think that's what he would talk to us about best. Other question? Gee, you've been very, very patient. Let me thank you for coming today. Please. Thank you very much.